All right, so in this video, we're going to talk about, in some sense, how many fractions there are. And in short, the answer is a lot. But in order to talk about that, we need to be able to find fractions in between two fractions. So this first question, I want you to find a fraction between 5/12 and 8/12. So pause the video now and see if you can find one. You don't need to find more than one, just one is fine. Okay, well hopefully you've seen, well, here we have 5/12 and here's 8/12, so 6/12 and 7/12 would be between them. So maybe you could pick 6/12 or maybe you'd pick 7/12. You could have other answers, but they're kind of the most obvious, I would say. All right, now that we did that, well, how about 6/11 and 8/15? We have to be a little more careful. Our denominators are different. So have a think about that. Pause the video now and see if you can find one. Okay, now that we're back, well, we can kind of use the idea that we used up here. Well, if they have the same denominator, it's really easy for the most part. So let's get that equivalent fraction where they have common denominators. So we'll multiply top and bottom by 15 on the left and top and bottom by 11 on the right. So 6 times 15 is 90. 11 times 15 is 165. 8 times 11 is 88. 11 times 15 is, of course, again, 165. Now, what is a fraction between 90 1/65 and 88 1/65? Well, that's kind of easy to see now that we have them with common denominators. How about 89 1/65? Okay, that's great. Okay, let's do this one. Find a fraction between 5/7 and 8/11. And I know some people are thinking, well, we just did a very similar one up in question 2, but this one will be a little bit different. There's going to be a slight hiccup. So pause the video now and try it. Okay, so let's play the same game as above. Multiply top and bottom by 11 on the left and top and bottom by 7 on the right to get fractions with a common denominator. So we get 5 times 11 is 55, 7 times 11 is 77, 8 times 7 is 56, and 11 times 7 is, of course, 77. Now it's a little harder. So we have 55 77ths and 56 77ths. So we can't do the exact same thing. We just pick one between them like we did in questions 1 and 2. But we might be able to be a little bit clever and have this idea still work. So again, if you didn't figure it out yet, pause the video now and see if you can use one of the ideas with fractions we've already talked about to make it so we can pick one in the middle. Okay, so the idea of equivalent fractions can help us here a whole lot. If we multiply top and bottom of both fractions by basically any whole number 2 or greater that we like, then we'll create, in some sense, enough room in our numerators to just pick a number in the middle. So let's go ahead and multiply it top and bottom by 2. And if we do that, we get 55 times 2 is 110, 77 times 2 is 154, 56 times 2 is 112, and 77 times 2 is 154. And I do want to stress here, 5/7 is the same quantity as 55 77ths, which is the same quantity as 110 154ths. They're all equivalent fractions. And similarly with 8/11ths, 56 77ths, and 112 154ths. So these represent the same quantities as these. And we can easily find a fraction in the middle now using the ideas from above. How about 111 over 154? Now, if we think about this method, there's nothing particularly special about any of these numbers. So if we think about it, and this is what we're going to prove on the next slide, we should be able to use this method to find a fraction between any two fractions. So let's go ahead and do that, but we need a very small result first. So here's the result, and it's nothing big. It basically says if you have two numbers, a and b, such that a is the bigger number, and they're both even, then they differ by at least 2. That makes sense. So that the difference between these two even numbers is definitely going to be even, and it can't be 0, so because a is greater than b, so it must be at least 2. And I'll just sketch the proof just by saying what I did. I don't want to write down all the details. So a sketch is just kind of like telling you how a proof would go, or not being completely accurate with the details. Oh, and one more thing, this word lemma. A lemma in mathematics, it's like a theorem, except it's kind of just a small result that's used in the proof of something bigger. So that's what a lemma means. Okay, so our sketch is as follows. Since a and b are even, a minus b is even. That's by, remember, theorem 2 from chapter 4. And since a is greater than b, that tells me that a minus b has to be greater than or equal to 2. So that's basically it. We didn't write it in painstaking detail, but it's pretty close to an actual proof. That's the rough idea. Okay, now that we have that lemma, what is the result we're going to prove? This is going to be our theorem. So, if a over b and c over d are, of course, fractions, where, let's say, a over b is the smaller fraction, then there is a fraction e over f such that it's in between. A over b is less than e over f, which is less than c over d. So this fraction e over f is in between. So we're saying there is always a fraction between two fractions. And our idea is basically going to be the same as the one that we did on the previous slide. So let's go ahead and prove it. Okay, so let's let a over b be less than c over d, so assuming our if part is true. Then by equivalent fractions, I'm going to multiply top and bottom of this fraction by d, top and bottom of this fraction by b. We get that AD over BD is less than BC over BD. Remember, A over B and AD over BD are equivalent fractions. They represent the same quantity, same as C over D and BC over BD. Now, we don't know for sure that there is an integer between AD and BC. Just like example 3 on the last slide, we might be in that scenario. But what we can do is, again by equivalent fractions, we can multiply top and bottom of both fractions by 2. That'll give us enough quote-unquote room in the numerator. So let's do it. So by equivalent fractions again, well, we'll multiply top and bottom of everything, both fractions, by 2. So we get that 2AD over 2BD is less than 2BC over 2BD. Okay, remember, A over B is less than C over D. These are equivalent fractions, so this still holds. Now, pause the video and see if you can see where we can apply the lemma we just talked about. Remember, the difference between any two even numbers is at least 2. Okay, now that we're back, let me scroll up here. So, if we look here, 2AD, these have the same denominators here, so we can just compare numerators. If these fractions are such that the left-hand one is less than the right-hand one, and the denominators are the same, it must mean that the left numerator is less than the right numerator. And, hey look, this is 2 times something, and this is 2 times something. So both the left and right-hand side numerators are even numbers. So that's how we can apply the lemma. So we can say, since 2AD and 2BC are even, of course they are, because it's something with a factor of 2. Here's the factor of 2 in both of them. Then we know that their difference is at least 2, which means that if I add 1 to this lesser numerator, then it's still less than 2BC. So, since 2AD and 2BC are even, then by the lemma, I know that 2BC minus 2AD is definitely greater than or equal to 2. So what does that tell me? So that tells me that if I just add 1 to the lesser one, then that is still less than 2BC. Since these differ by at least 2, if I add 1 here, it's still not as big as the right-hand side. Okay, so that's great. So our fraction, so that tells me that the smallest fraction, 2AD over 2BD, if I add 1 to the numerator, obviously the numerator gets bigger, so the fraction gets bigger. And it's still less than 2BC. So the middle fraction is less than the fraction on the right. They all have the same denominators. 2AD is the smallest numerator, 2BC is the largest numerator, and 2AD plus 1, well, it's definitely greater than 2AD. And because 2bc minus 2ad is greater than or equal to 2, these differ by at least 2, then if I add 1 to the smaller one, it's not as big as the larger one. So there we go. So E over F above is 2AD plus 1 over 2BD. So there is our fraction that's in between the other two fractions. And we're done. So what's the upshot to this? Well, let's have a look. So here's, say, fraction a over b, and here's c over d on a number line. And we found a fraction between them, e over f. So I'm going to put that in. Let's say it's somewhere around here. Whatever. Okay. But now that I found a fraction between a over b and c over d, well, I can find a fraction between a over b and this e over f. Why not? So here's that fraction. And I can find one between e over f and c over d. Here's that one. And I could pick any two fractions I like here. I could find a fraction between these two now. So that fraction. And a fraction between these two, that one. And the next two, and the next two. And I could keep going. And I could find fractions between any two fractions that I like. I could keep continuing this if I want. Maybe I'll even do one more layer. So if you think about this, what does this mean? Well, between any two fractions I like, how many fractions can I find? I can find infinitely many. So this is going to be called a corollary. Don't worry about the names, but this is just a mathematical result that comes from just a previous one. I think I have that spelled wrong. C-O-R-O. Corollary. There are infinitely many fractions between, and that's just a dot, that's not a apostrophe, between any two fractions. And the word we use to describe something like that, where there's infinitely many numbers between two numbers, we call that dense. So that means thus fractions are dense on the number line. Pick any interval on the number line you like, it doesn't matter which, you'll find infinitely many fractions in there. And I guess I'll just sketch this proof. All we're going to do is we're going to apply previous theorem over and over again. Over and over. And that's basically what's going on. The diagram above kind of explains what's happening in kind of a visual sense, and if we were to write out an actual proof, it would basically be writing this, but just in detail. So that's really cool. The fractions are different than the integers. The integers are not dense on the number line. You can find an interval, in fact, take any interval that you like, pretty much, and there are finitely many integers in it. But fractions, it's different. Fractions, there is always infinitely many. So fractions are dense on the number line, integers are not.